Hello, and thank you for joining us for today's webinar, Myth-Busting 3D Prototypes. Does high resolution equal high accuracy? My name is Fred Fisher, and I'm a Director of Business Development with Stratasys, and I'll be your host for today's event. For those of you who aren't familiar with our company, Stratasys makes additive manufacturing systems that produce prototypes and production parts directly from three-dimensional CAD files. Stratasys manufactures and markets two lines of systems, Dimension 3D printers and Fortis 3D production systems that use our patented FDM technology to produce those parts. We also operate Red-Eye On-Demand and online rapid prototyping and direct digital manufacturing service. In this webinar, you'll learn when and why accuracy is critical to three-dimensional prototypes, the difference between resolution, accuracy, and repeatability, and when you should consider accuracy while evaluating additive manufacturing systems. And now I'd like to introduce our speaker for today, Bonnie Meyer. Bonnie has a mechanical engineering degree from Michigan Tech and more than a decade of experience in application engineering. During that time, she's worked with multiple additive manufacturing technologies, including both resin-based processes as well as fused deposition modeling. Bonnie has authored dozens of technical papers applying additive manufacturing techniques to speed product development and improve manufacturing efficiency. As a senior applications engineer at Stratasys, Bonnie manages a team that works directly with users to help them maximize their productivity and profitability with additive manufacturing. Now, without further ado, Bonnie, the floor is all yours.
Thank you, Fred. As Fred mentioned, I'm Bonnie Meyer. I've been an application engineer for 11 years. Speaking from experience, I've seen the accuracy myth in action more times than I can count. But myth may be a bit strong. Let's say accuracy misconception. The misconception is that accuracy can be determined through unrelated factors like resolution and layer thickness, and that additive manufacturing part quality is linked to appearance. I will spend a few moments today to correct the misconception, to dispel the myth and shed some light on the truth. I've seen it over and over. Engineering professionals judging the book by its cover. When they get the first glimpse of an additive manufacturing part, they tend to assume the quality of the part is based on its appearance. A pretty part with smooth surfaces, the calipers stay in the drawer, accuracy is assumed. A part like that is shown in the top picture. A part with visible layers, throw the calipers on the part and start looking for dimensional inaccuracies, fully expecting to find that the part doesn't meet specifications. It's not until they assemble the parts they discover the true accuracy. They learn once again that appearance and resolution have little bearing on accuracy. If it did, the engineering scale on the right would be the more accurate of the two. Imagine these two rulers. One has 32 tick marks per inch, like the one on the right. And the one on the left, the green one on the left, has 4 tick marks per inch. Most people would assume that the one on the right, with 8 times more tick marks, is more accurate. However, more marks does not make it more accurate. The accuracy of the ruler is directly related to how close the overall length is to the specified dimension, in this case 12 inches. The same is true in additive manufacturing. The accuracy of a part is a result of how close the part is to the specified dimension, not how many layers make up a given feature or distance. To show the disconnect between accuracy and resolution in the additive manufacturing industry, consider these two parts. Which is more accurate, the one on the left or the one on the right? Let's take a closer look. It's impossible to tell, right? If we're honest with ourselves, we'd have to admit that we tend to let the myth stand. A little later, we'll see the answer. The additive manufacturing industry is filled with accuracy claims. Many are unsubstantiated. Some will lead those that are misinformed to believe that 600 dpi XY resolution or a 5,000th inch spot size correlates to exceptional accuracy. This is simply not true, as I will prove with hard data from exhaustive analysis. Let's take a moment to do a quick overview of some terms. Resolution specifies the smallest feature that a system will produce. For additive manufacturing, there are two types of resolution. The first is in the XY plane. For a raster process, this is the space between droplets. For a vector process, it's the spot size, or the diameter of a laser beam or the extrusion. The second is in Z, or vertical axis. For all processes, this is the layer thickness. Accuracy is how closely a part matches the intended dimensions. Precision is how closely the system gets to its target spot and is often confused with accuracy. And repeatability is the degree of variance between parts. Each of these factors may influence the quality of your additive manufacturing parts. However, resolution only influences accuracy if it results in features that are oversized or omitted. And don't forget, quality is always in the context of the application. The application dictates which of these parameters define quality. And there's one other variable that's critical in assessing quality, and that's stability. Stability is the ability to maintain or hold accuracy over time. But we'll go into more of that later. So by no means am I discounting the value of resolution. There are applications where it's more important than accuracy, applications where quality is a function of resolution. A few that come to mind are show models, gorgeous pieces painted and decorated to look like a production part. Here, Z resolution or layer thickness can be a factor. For thinner layers produce smoother surfaces, which means less post-processing. Fine-featured parts is found in jewelry. These are very detailed with fine features that demand a very high resolution, and also tooling or patterns. But really, how frequently is this required for your applications? For functional prototypes, fixtures, and finished goods, accuracy takes precedence, and that is paired with repeatability when you need more than one. For commercial or industry parts that are routinely injection molded, thermoformed, investment cast, or die cast, for example, product designs tend to avoid tiny features and paper-thin walls. So in this case, an additive manufacturing technology that replicates features larger than 20 thousandths of an inch will get the job done, as long as it manufactures all those features to the same stringent standards, namely tolerance and repeatability, as the traditional manufacturing process. And those stringent standards are never expressed in dots per inch. A similar myth exists in the inspection or the quality arena. Think back on our 12-inch ruler example. Expand that to a three-dimensional measurement system. One method or tool measures a small number of points, but measures down to, say, 1/10,000th of an inch. While another method may have hundreds or even millions of measurement points, but may only measure to 2/1000th of an inch. In this case, some want to believe that more points mean more accurate measurements. It's not necessarily true. The accuracy of the measurement device is a result of the device's capabilities, not the number of points it measures. Choose a measurement tool or technique that has an appropriate resolution for your application requirements. In the remainder of this study, we'll use a highly accurate 3D laser scanner to compare different parts. So back to the housing we saw earlier. You tell me which is more accurate, the one on the left with 600 dpi and 1.5 thousandths layers, or the one on the right with 10,000th inch layers. Take a look at the color maps. 3D scanning data that is color-coded point by point to show how true to the design the additive manufacturing parts are. The red areas are oversized by 20 thousandths of an inch or more. The purples are undersized by 20 thousandths of an inch or more. The green areas are within plus or minus 5 thousandths of an inch, and the little bit of yellow on the right-hand image, it's about 7 thousandths of an inch oversized. This is just one example that shows resolution does not equal accuracy. As you can guess, the one on the right was printed with fused deposition modeling. But it's from a Stratasys entry-level printer, the U-Print, which is optimized for printing concept models and prototypes. I will show in just a bit the accuracy of the production-oriented Fortis line that is engineered for manufacturing applications. This will be demonstrated by thorough analysis that no others, to my knowledge, have published. While FDM technology may not be ideal for ultra-high resolution parts like jewelry, It is engineered to meet the stringent accuracy demands of functional prototypes, fixtures, and finished goods. The FDM system resolution, layers from 5,000ths to 20,000ths of an inch, and extrusions that produce features as small as 16,000ths of an inch. For functional prototypes and finished goods, another important consideration is stability, which we defined previously as accuracy over time. Many parts from additive manufacturing systems have service lives that extend beyond hours. With service lives of days, weeks, or even years, the accuracy of the part out of the system is just the start. It's equally critical to evaluate accuracy over time. Well, there's a number of factors that may affect dimensional accuracy of an additive manufactured part over time. Residual stress. Some processes impart stresses that over time will alter the part. An example of residual stress would be a part that might warp as it cools when it's taken out of the system. The most obvious example is a part that was originally flat and now it's warped, as shown in the picture on the slide. Moisture. Some additive manufacturing materials are hygroscopic. They absorb moisture from the air. This may cause the part to swell, warp, or result in mechanical property changes. An example would be a part that is exposed to high humidity environments, like found in many warmer climates of the world. The ambient moisture can cause the part to warp or change shape. Temperature. Like moisture, heat or cold can alter the dimensions. Not as a function of the coefficient of thermal expansion, but as a result of the release of stresses, or even a low glass transition temperature that causes the part to bow, twist, and warp with modest temperatures. An example might occur when a part is shipped. The extreme temperatures, hot and cold, that the part will be exposed to can potentially warp the part with some technologies that have a lower glass transition or service temperature. UV exposure. Especially for photopolymers, UV exposure can lead to additional curing, which may change dimensions. Thermoplastic and metal parts from additive manufacturing technologies are generally much less susceptible to the factors listed. These materials are significantly more stable and can survive more extreme mechanical, chemical, and thermal conditions. Thermoplastic and metal part applications can extend beyond the temperature and humidity-controlled office environment and into more applications. Your last consideration when producing more than one part for functional testing or a batch of finished goods is repeatability. It's common knowledge that additive manufacturing processes in general tend to have low repeatability. There's variance between the parts, whether in the same batch due to placement in machines, batch to batch, different runs on a machine, or machine to machine. This is perhaps the most significant obstacle to manufacturing with additive technologies. When making finished goods, process control is critical. Variance between parts, lots, and production facilities is unacceptable. But FDM is different, and I have the data to prove it. We conducted extensive studies to determine the process capabilities with analysis of repeatability. Here are the test conditions. Over 100 parts were built and close to 3,000 measurements were taken. Most importantly, no adjustments were made to the machines to dial in the accuracy. But in the real world, you would be able to use sample values as guidance to adjust controls or the model to hit target values. To do this, though, the process must be repeatable. Here's what we found. In the language of quality control, we had a standard deviation of only 27 ten-thousandths of an inch, centered on a mean of 34 100,000ths. You can see in this histogram, that means the vast majority of dimensions fell within minus 2,000ths to plus 3,000ths. For those who don't usually look at repeatability this way, a normal distribution curve that's high, tight, and centered on zero is what you want. And this is what we have. To look at it another way, 80% of all dimensions were within plus or minus 3,000ths of an inch, and 95% were within plus or minus 5,000ths of an inch. I think you'll agree that this is proof that FDM delivers accurate parts with predictable results and very high repeatability. Others may claim it. Stratasys invested in the study to prove that FDM can be your alternative for finished goods manufacturing. And to prove stability over time, we dug out the sample parts from the study, which were just tossed in a box to take a few measurements. The results are shown here, and as you can see, there was very little change over time. The results show that FDM is accurate, predictable, and repeatable. I hope I've given you enough proof to dispel the accuracy myth, enough proof to show that resolution does not always translate to accuracy. And stability of the part is often dependent on the material used to produce your part. I also hope that if confronted with a resolution or accuracy claim, you'll ask for proof. If you're conducting a thorough system review, measure when you receive the part and measure it over time. And I suggest 3D scanning or color mapping or another high-resolution measurement technique. Get the whole picture, every feature, every aspect of dimensional accuracy. And finally, maybe most important, work with your teams to determine what your true wants versus needs are when considering an additive manufacturing part or system. We generally find those that are the most satisfied with their technology choice, both initially and in the long term, are those who purchase based not just on their wants, but on the real needs of their application.
All right, Bonnie, excellent advice and content. I want to remind you that in a minute we'll have a chance to take questions if you may have those. So in the meantime, if you do have questions, be sure to submit those through the Q&A panel. In addition, I wanted to let you know that after today's event, you can find this recording, request a sample part, and download other relevant materials on stratasys.com/accuracy. All right, well, it looks like during the presentation we had a couple questions come in, and I'd like to take some of these now. Let's look at the first one. It looks like Todd asks, as an operator of an RP system, are there ways to improve accuracy on the actual output?
Well, that depends on the technology and the type of system you have. In general, 3D printers are a lower cost, and they're optimized for ease of use. So the user is not going to be exposed to quite as many parameters to adjust the accuracy. 3D production systems in general are optimized for higher requirements, so the user would be exposed to more controls and more features and more likely to dial in their accuracy.
Mm-hmm. Okay, good. All right, interesting. Looks like we have another one from Carl. He asks that the accuracy that you outlined seems great for the test parts and the examples, but is it really going to hold true for my part and my application, if not in a controlled environment?
Well, that's a good question, and one we receive quite a bit. We always recommend that you build a benchmark, build one of your parts on the technologies you're looking at, and test their claims. There's no better way to see if their claims hold true than to build one of your parts and see for yourself.
Mm-hmm. Okay, good. That's some good questions. Let's keep these coming in. Looks like here's another one from Christine. It says, once I've got a part in hand, are there ways to improve the accuracy after I have it in hand?
Well, generally once the part comes out of a system, regardless of which technology or which material you're using in, there are ways to kind of dial in the accuracy. If it's too small, you can add material, you can add Bondo or fillers. If the part is a little bit too large in an area, you can remove material by sanding or machining. But again, consider stability. It's the stability of a part is largely a function of what material you've used. Mm-hmm. So you want to minimize the exposure to environments that are beyond the part's tolerance.
Okay, good. Yeah, excellent information. It looks like we have time for one more question, and Ryan asks, it says, I often build parts that are larger than my system's envelope. What are there best practices to maximize accuracy when bonding two or more parts together?
Well, again, it depends on the technology you're using, but regardless of the technology, there are some best practices for bonding parts. Typically, you want to leave a clearance between the sections so it's easier to fill in and sand that joint smooth. Build the parts in the same orientation regardless of which system and which technology you're using. And a joint you want, rather than just a straight butt joint, you would like a dovetail, sawtooth, tongue and groove, something to help lock the different parts together. It's also important to consider machine-to-machine repeatability if you're looking at purchasing more than one system. The non-repeatable technologies, you're you're kind of forced to build on one system. But the repeatable technologies, you have a little more convenience or even luxury to build on different systems because of that repeatability, and that can really impact your throughput.
Mm-hmm. Okay, good. Well, it looks like we're just about out of time for today. I'd like to thank you all for your great questions. If we didn't have a chance to get to your questions on the call, we'll make sure to follow up with you afterward via email. Once again, as a reminder, you can find this recording, request a sample part, and download other relevant accuracy materials on stratasys.com/accuracy. We'd like to thank each of you for your attention during this presentation, and now I'll turn it over to our operator who will close out our session.